Hello everyone, good morning. Myself, Dr. Shubhankar Sen, an Associate Professor in the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the first lecture of the 7th module of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In the previous weeks, we mostly dealt with the elliptic partial differential equations. Those are the equilibrium problems characterizing the boundary value problems. In today's class, we shall begin with the transient-like problems or the marching problems that are characterized by parabolic as well as hyperbolic partial differential equations. Under the parabolic partial differential equations, we shall consider the transient heat conduction equation. We shall derive the weak form of the transient heat conduction equation, and then we shall introduce the concept of mass matrix that will be coming in the element level matrix equation system, and then we shall illustrate the different time integration schemes, namely the forward or explicit Euler scheme, the backward or implicit Euler scheme, the Crank-Nicholson scheme, as well as the Galerkin scheme. So we begin with the numerical integration by using the Galerkin finite element formulation for the unsteady or transient parabolic partial differential equation related to heat conduction. Marching or propagation problems. These are unsteady state problems in general. So these are initial value problem or initial boundary value problems. Marching problems are governed by parabolic and hyperbolic PDEs. So we consider a parabolic PDE in connection with the heat conduction phenomenon. Heat conduction phenomenon. Let temperature is a function of space and time, be the degree of freedom. The energy equation is expressed as rho Cp del T equals to K del square T plus the source term. Here we represent the variable as x bar for the coordinates. It is a vector quantity. So this is the unsteady term. This is the diffusion term. And this is the source term. So this equation is in vector form. Vector or coordinate form of the exact or continuum equation. This equation is valid on a domain omega. Omega is the fixed spatial domain that does not vary with time. So we consider a domain that is fixed with respect to time, and also its boundary gamma, it does not change with time. So this is the strong form of the governing equation. This is coordinate free. Let tau represents the time domain such that the time t, it belongs to 0 to tau. Now, the strong form may be expressed as del t equals to alpha del square t plus s tilde x bar over omega cross tau. Here alpha equals to k by rho Cp equals to thermal diffusivity of the material, and s tilde x bar equals to sx bar divided by rho Cp. We have temperature is given along gamma g and minus k del t del n equals to q0 along gamma h. These boundary conditions are independent of time. So this is the strong form of transient heat conduction equation subject to EBC and NBC. Now we derive the weak form of this governing equation. So derivation of the weak form using the statement of method of weighted residual, we have integration over omega e w r th d omega e equals to 0. Here this is our domain omega, this is our domain boundary gamma, and this is an arbitrary finite element whose domain we denote by the symbol omega e and boundary as gamma e. So here R of approximate solution for temperature Th, this is given as del Th del T minus alpha del square Th minus S tilde is not equals to 0. Substituting this in the statement of MWR, we get this gives integration over omega e w into del Th del T minus alpha del square Th minus S tilde d omega e is equals to 0. Now, dropping the superscript h from Th and applying Galerkin FEM, we obtain here this is certainly equal to 0. Integration over omega e w into del T minus alpha del square T minus S tilde d omega e equals to 0. Here perform integration by parts using the Green-Gauss theorem, we obtain integration omega e w del t d omega e minus integration over omega e alpha w del square t d omega e minus integration over omega e w s tilde d omega e equals to 0. This gives us integration over omega e w del t d omega e minus alpha. This thermal diffusivity, it is a constant material property. We can make this assumption. Then we have integration over omega e w del square t d omega e equals to integration over omega e w s tilde d omega e. Now this s tilde, it is the source term, a known term, which we can conveniently shift to the right hand side. This integration gives us integration over omega e w del t del x d omega e minus alpha into minus integration over omega e gradient of temperature into d omega e plus boundary integral over gamma e w del t del n d gamma e. This is equals to integration over omega e w s tilde d omega e. This can be written as integration over omega e w del t del x d omega e plus alpha into integration over omega e gradient of w dot gradient of temperature d omega e equals to integration over omega e w s tilde d omega e plus alpha into boundary integral over gamma e w del t del n d gamma e. Now this is the weak form of the transient heat conduction equation. Weak form of the given transient heat conduction equation. Here we have separated the bilinear terms and the linear terms. So this is the portion in the left hand side. This is the BWT or the bilinear term, and this right hand side portion, this is the linear term. This is the linear term containing only W, and we separated these two items as BWT and LW. Now for Galerkin approximation, put W equals to psi IE, and the trial solution is expressed as T equals to summation TJE psi JE plus summation TBE psi BE. Here J equals to 1 to NEN. In the second portion we have B belongs to eta G. Now let us discuss about the trial solution little more. Here this is time derivative, this is also time derivative. The trial solution t x bar time equals to unknown part plus known part from EBC. This unknown part, this is given as summation over j varying from 1 to number of nodes per element. TJE, this is a function of time only, into psi je, this is a function of space only, plus summation of TBE, psi BE. Psi BE is a function of space only. Here B belongs to eta g. So this is the EBC contribution. This is important to note here that in the previous discussions, in the previous weeks, we have already taken the shape function to be a function of space only. So here also we are taking the shape function only to vary with space, since we are dealing with a degree of freedom that is varying with space and time both. So to maintain the unsteady nature of temperature, we have to take the nodal value as a function of time. So here the nodal value is considered to be a function of time. The weak form which we already had, that is the weak form is given as integration over omega e w del t del x d omega e plus alpha integration over omega e gradient of w dot gradient of t d omega e equals to integration over omega e s tilde d omega e plus alpha boundary integral over gamma e w into del t del n d gamma e. So we substitute the trial solution and the weight function by the approximate quantities. Substitution of the trial solution and W equals to psi IE for GFEM leads to integration over omega e psi IE. This is del t. The trial solution was TJE time psi je plus TBE constant at the boundary psi BE. B belongs to eta g, j equals to 1 to nen d omega e plus alpha integration over omega e gradient of psi IE dot gradient of the trial solution summation TJE psi je, j is varying from 1 to nen plus summation of TBE psi BE, B belongs to eta g d omega e equals to integration over omega e psi IE s tilde d omega e plus boundary integral over gamma e psi IE alpha del t del n d gamma e. This can be simplified as summation over j equals to 1 to nen integration over omega e psi IE psi je d omega e del tje, a function of time, del t plus summation over b belongs to eta g psi ie integration over omega e psi be d omega e del tbe del t. We are keeping this term as a general term. This tb, if it is a function of time, then only this del tbe del t, this term will exist, else this term will have no contribution, plus alpha into summation over j varying from 1 to nen gradient of psi ie dot gradient of psi je d omega e tje plus summation over b belongs to eta g alpha integration over omega e gradient of psi ie dot gradient of psi be d omega e into tbe equals to integration over omega e psi ie s tilde d omega e plus boundary integral over gamma e psi ie into alpha del t del n d gamma e. If we look into these terms, we can see that the first term and third term, they are containing the unknown terms, and the remaining terms, they are the known terms and contributed by the boundary conditions of essential type. And because of this, the second term and fourth term in the left hand side, they will be shifted to the right hand side. The second and fourth terms of LHS are due to EBC and hence will be shifted to the right hand side. Here it is integration over omega e. The above weak form can therefore be further simplified as summation where j is varying from 1 to nen integration over omega e psi ie psi je d omega e del tje del t plus summation over j equals to 1 to nen integration over omega e gradient of psi ie dot gradient of psi je d omega e into tje equals to integration over omega e psi ie s tilde d omega e plus boundary integral over gamma e psi ie alpha del t del n d gamma e. Now we bring the left hand side portions due to EBC to the right hand side. Both of these terms are positive terms, so they should be connected with the negative signs. Minus summation over b belongs to eta g integration over omega e gradient of psi ie dot gradient of psi be d omega e tbe minus summation over b belongs to eta g. We have one unsteady term due to EBC. This is psi ie. Then we have psi be d omega e del tbe del t. So here we shall have the alpha. Now we introduce certain symbols for the integrands. Let us define integration over omega e psi ie psi je d omega e equals to mij alpha into integration over omega e gradient of psi ie dot gradient of psi je d omega e equals to kij. Then we define integration over omega e gradient of psi ie dot gradient of psi be d omega e. Here also we shall have the alpha. This we can write it as k ibe. Similarly, the last term we can represent as integration over omega e psi ie psi be d omega e equals to m ibe. Here Mij, this is known as the consistent mass matrix that arises due to discretization of the unsteady term. With the introduction of these symbols, the above equation we can represent in the following form as summation over j equals to 1 to nen mij del tje del t plus summation over j equals to 1 to nen kij tje equals to integration over omega e psi ie s tilde d omega e plus boundary integral over gamma e psi ie alpha del t del n d gamma e minus summation over b belongs to eta g kibe tbe minus summation over b belongs to eta g m ibe del tbe del t. This first portion, this is due to the unsteady term. This is the stiffness matrix. Due to conduction or diffusion. This is the source term in the right hand side, the first term. The second term in the right hand side, this is the NBC or natural boundary condition contribution. The third term in the right hand side, this is a contribution due to EBC, and the fourth term, this is due to time dependent essential boundary condition contribution. So this is contribution due to unsteady or time dependent EBC. Here alpha was missing. So we can rewrite this equation as this equation can be expressed in a compact form as summation over j equals to 1 to nen mij del tje del t plus summation over j equals to 1 to nen kij tje equals to fie, ith algebraic equation for element E, where Fie, the element level load vector, this is integration over omega E psi ie s tilde d omega E plus boundary integral over gamma E, this is psi ie alpha del t del n d omega E minus summation over b belongs to eta g kibe tbe minus summation over b belongs to eta g mibe del t be del t. This is the ith ordinary differential equation for temperature in time. So this equation, this is actually an ordinary differential equation, since the above equation is an ODE, we can represent it as summation over j equals to 1 to nen mij dtje dt plus summation over j equals to 1 to nen kij tje equals to fie, or in matrix form we can write it as me dte dt plus ke t equals to fe. So this particular form is known as the semi-discrete form of the given strong form. So this is the semi-discrete form of the given strong form. The semi-discrete form is obtained after spatial discretization. In unsteady problems, we generally discretize with respect to space first, followed by time integration. The term time integration, it represents discretization of the unsteady term. Time integration amounts to discretization of the unsteady term dt. So now we have the semi-discrete form of the governing equation. Here, if the computational domain is not changing with time, then this semi-discrete equation can be further simplified by using finite difference method for the time derivative. When omega does not vary with time, the unsteady term dt is conventionally discretized using FDM. Therefore, FEM for space discretization and FDM for time discretization when omega and gamma are fixed relative to time. If omega and gamma both vary with time, we can use FEM for both time and space discretization. The space-time FEM formulation is one such approach where FEM is used for space as well as time discretization. Our semi-discrete form is given by ME DTE dt plus KE TE equals to FE. So we shall use finite difference method for time integration. Now there are four basic approaches for this time integration under finite difference. Time integration under FDM, we have the explicit or forward Euler scheme, we have implicit or backward Euler, we have Grant-Nicholson scheme, and then we have Galerkin scheme. So the first case is conditionally stable. Here the results, the solution, whether it will converge or not, it is based on conditions. So we say that this is conditionally stable. The second, third and fourth, these are coming under the group of unconditionally stable. Unconditionally stable but not unconditionally accurate. For the explicit scheme, the order of accuracy is first order. So for explicit scheme, the order of accuracy is order of time step size. For the implicit scheme, the order of accuracy is also first order. It is order of delta t. For the Grant-Nicholson scheme, the order of accuracy is second order. So this is order of delta t whole square. And similarly, for the Galerkin scheme also, the accuracy is in second order in time, order of delta t whole square. Now we illustrate the implementation of all four schemes. Illustration of the differentiating schemes. So before showing this, we convert the element level equation into the global level equation. So convert the element level semi-discrete equation to global semi-discrete equation. So ME DTE dt plus KE TE equals to FE. It is represented as M into dt dt plus K into T equals to capital F. So this is global consistent mass matrix, assembled or global stiffness matrix, and here it is global load vector. Now let P represents number of time step and delta T size of time step. We introduce these two variables to illustrate the differentiating schemes using the finite difference for the time derivatives. The forward Euler scheme or explicit scheme. So for this case, the mass matrix, here this dt we represent it as temperature at the P plus 1th level minus temperature at the Pth level by delta T plus the stiffness matrix K, it is constant, and then the temperature associated with stiffness matrix, we considered it at the Pth level or the current level, and then the load vector is also at the current level. So these are known terms. So only Tp plus 1, this is unknown, Tp is also known. So we have an initial condition. We have an initial condition for first order transient problems. So we can take as temperature at any location at time t equals to 0 as the T0 vector. So this represents our initial condition, and this initial condition is compulsory for the transient problems. We take that our mass matrix is independent of time. This is independent of time. Then we can simplify this expression as mass matrix into T of P plus 1 equals to delta T, the load vector at the Pth level, minus delta T into global stiffness matrix into the known temperature at the Pth level plus the mass matrix into temperature at the Pth level. So in this case, we see that every quantity in the right hand side they are known. So this is known. Here mass matrix is known and the temperature with index p plus 1, this is the only unknown. It means that if we simply invert the consistent mass matrix in the left hand side, we can easily find the load vector at the p plus 1th level. So this gives us T at p plus 1th level equals to inverse of mass matrix into delta T Fp minus delta T into stiffness matrix into temperature at known level plus the mass matrix as well as the known temperatures product. But our mass matrix is not a diagonal matrix. The consistent mass matrix is not a diagonal matrix and hence its inversion requires involved calculations. To simplify the calculations, the mass matrix M is diagonalized. The diagonalization process is known as mass lumping. The mass lumping can be obtained using row sum lumping and proportionate lumping. The element level mass matrix is found to be symmetric, positive definite, diagonal dominant, and linearly independent. So Mij equals to integration over omega e psi I psi j d omega e. So for two noded bar elements, Me equals to Mij equals to M11e, M12e, M21e, M22e equals to delta x by 3, delta x by 6, delta x by 6, delta x by 3. So we get here, this is delta x by 6 to 2, 1, 1, 2. So this is the consistent mass matrix. Therefore, this assembled mass matrix, when this is generated by assembly operator of the element level mass matrices for all the elements, M is non-diagonal. This element level mass matrix ME, it can be diagonalized as ME after row sum lumping looks like ME row lumped equals to delta x by 3 plus delta x by 6, 0, 0, delta x by 6 plus delta x by 3 equals to 6. Here we have 2 delta x plus delta x, 0, 0, 2 delta x plus delta x divided by 6. This is equals to 3 delta x by 6, 0, 0, 3 delta x by 6. So this gives us ME row lumped equals to delta x by 2, 0, 0, delta x by 2 equals to delta x by 2, 1, 0, 0, 1. Since ME row lumped is a diagonal matrix, the assembled row lumped matrix will also be a diagonal matrix. Once we have the assembled matrix as a diagonal matrix, we can easily invert it. The explicit scheme is conditionally stable, implying that delta t or time step size should not be large and delta t should be obtained from stability criterion to avoid oscillatory solutions or divergence of results. So this forward Euler scheme, this is the explicit scheme is first order accurate in time, or its accuracy is order of delta t. Now we go for the implicit scheme or the backward Euler scheme. So case 2, implicit scheme or the backward Euler scheme. Our assembled equation is m dt plus kt equals to f. This is semi-discrete assembled equation. Using implicit scheme, we can write it as m temperature at P plus 1 minus temperature at pth level divided by delta T plus the stiffness matrix into temperature at p plus 1th level equals to load vector at the p plus 1th level. Now we take the unknown terms in the left hand side and shift all the known terms to the right hand side. In this case, we see that the contribution due to the stiffness matrix is an unknown term and it will be maintained in the left hand side. So here this acts as an unknown term. So we can simplify this as m into T at p plus 1 minus m at temperature at the pth level plus delta T into stiffness matrix into temperature at p plus 1th level equals to the load vector at the p plus 1th level. This gives us m into temperature at p plus 1th level plus delta T into stiffness matrix into temperature at p plus 1th level equals to load vector at p plus 1th level plus the mass matrix into the known temperature. So the implicit schemes are unconditionally stable. Its order of accuracy is order of delta T. However, unconditional stability does not imply unconditional accuracy. Therefore, we can use delta T value higher than that used in explicit scheme, but delta T should not be very high. Case 3 is the Crank-Nicholson scheme. The Crank-Nicholson scheme, this is also an unconditionally stable scheme, and this is a second order accurate scheme. This is obtained by taking average of the forward Euler and the backward Euler scheme. This is unconditionally stable and second order accurate in time. This is obtained by taking average of the explicit and implicit schemes. So our semi-discrete form is m dt plus kt equals to f. So explicit formulation, it gives us explicit scheme gives m t at p plus 1 minus t at p by delta t plus k t equals to F. Implicit scheme gives M T at P plus 1 minus T at P by delta T plus K at T at P plus 1 equals to F at P plus 1. So if we add both of these schemes, we find it 2 into M into T at P plus 1 minus T at P by delta T plus stiffness matrix into temperature at pth level plus temperature at P plus 1th level equals to the load vector at the pth level plus the load vector at the P plus 1th level. There will be delta T. There will be delta T. M into T at P plus 1 minus T at pth level plus delta T by 2 into K into T at pth level plus T at P plus 1th level equals to F at pth level plus F at P plus 1th level. So this can be written as M into T at P plus 1th level minus M into T at pth level plus delta T by 2 into K into T at pth level plus delta T by 2 into K at into T at P plus 1th level equals to F at pth level plus F at P plus 1th level. This can be written as the mass matrix plus delta T by 2 into stiffness matrix into temperature at P plus 1th level equals to mass matrix minus delta T by 2 into the stiffness matrix into temperature at the pth level plus the load vector at the pth level plus the load vector at the P plus 1th level. So this will also be divided by 2. So this is associated with half. So this is divided by 2. So this is the final form of the Frank-Nicholson formulation. All these three formulations, they are actually special cases of a generalized formulation. So we define it as generalized alpha parameter formulation. Case 4, generalized alpha parameter formulation. The full discrete form given above may be rearranged as mass matrix plus alpha delta T into stiffness matrix, temperature at unknown level equals to mass matrix minus 1 minus alpha into stiffness matrix into known temperature plus 1 minus alpha into load vector at the pth level plus alpha into load vector at the p plus 1th level. So this is the generalized alpha family of fully discretized equation. So if alpha equals to 0, we get explicit scheme. If alpha equals to 1, we get implicit scheme. If alpha equals to half, we get Crank-Nicolson scheme. If alpha equals to 2/3, we get Galerkin scheme. So the value of alpha, it lies between 0 and 1. So the first two schemes, the explicit and implicit schemes, their order of accuracy is first order. So this is order of delta T. The last two schemes, namely the Crank-Nicolson and the Galerkin scheme, they are second order accurate uptime. So it can be represented as order of delta T whole square. Here delta T is missing. Here also delta T should come multiplied with delta T. The second bracket, it should be positioned here. There will be a second bracket here. And then the delta T should come here. We conclude today's class here. In today's class, we have shown semi-discrete and fully discrete equations from strong form of transient heat conduction equation. We introduced the concept of consistent and lumped mass matrices. The explicit, implicit Crank-Nicolson and Galerkin time integration schemes have been discussed. For today's class, I suggest the books by Professor T.J.R. Hughes as well as Professor J.N. Reddy. Thank you very much for attending this lecture.